Okay, so we talk about binary search tree sorting. I mean, how binary search tree can help us to have a sorting algorithm. So before that, let us talk about what is a binary, recap the binary search tree. Binary search tree, or in short it is called BST. So it is basically a tree and it has some property, binary search property. What is that? It is, suppose we take, so this is a tree, suppose we take any node over here in this tree, this is key value is x. Now we consider the left subtree rooted at this, right subtree rooted at this. Now binary search tree means all the key value over here must be less than x, all the key value must be greater than x. So this is the property. So if they are distinct, then it is must be strictly this. So this is the property of binary search. So a binary tree which is having this property is called binary search tree. So if all the elements in the left side of the tree is less than x, and all the elements in the right side of the tree must be greater than x. Okay. So there are some good tree and bad tree. So what are the good tree? So suppose we have a tree like this. This is a good binary tree. Why? Because it is balanced. This one is good tree. Good in the sense it is balanced, height is log n. So if there are n nodes, height is log n. So this is a balanced tree. And what is the bad tree? Bad binary tree like this. If we have this, so say height is n. Okay. So this is a bad tree because it is not balanced tree. So why balanced tree is good? Because we can do some search or we can do some query in a height time, and if height is log n, then it is a log n time. So that's why it is good to have a balanced tree. Okay. So now we'll talk about so BST sort, binary search tree sort, how we can use the binary tree to have a sorting algorithm. So let us just talk, write this as BST sort. So we have given n numbers, we can sort them by using the binary search tree. So this is BST sort. We have given n numbers, or we have given an array of size n. So what we do? First, our T is empty. We are initializing a tree, binary search tree, empty, and then we will form the tree. So we just, for I is equal to 1 to n, we insert this node into the tree. So this is BST insert basically. We insert this AI into the tree, and then we will do the Inorder traversal of the tree. So this is after this we form the tree, we form the BST. So we will talk about how the BST insert will work. We form the BST, and then so to form the BST, basically we start with the root until we reach to a nil or the leaf node. If tree is initially empty, then the first node will be the root, and in the subsequent step, so if we start with the root, if the element is less than that, we go to the left side of the root, left subtree, otherwise we go to the right subtree, and this way we continue until we reach to a nil or leaf node. Once we reach to a nil, we insert that node there. So this is the basically BST insert, and then we do the Inorder tree walk. Inorder tree walk of this tree. Inorder tree walk means we first print the, this is basically the way to print a tree or a traversal, tree traversal. So we first print the left subtree, then the root, then the right subtree. Okay. So that way we just visit the all the elements of the tree. So this is one. So there are in order, pre order, post order. Okay, so so this is the way. So in order, if we do the Inorder traversal, then we will get the sorted one. So so let us take an example. Suppose we have some number, say 3, 1, 8, 2, 6, 7, 5. Okay. Suppose this is our A array. This is our given numbers. There are how many numbers? 1, 2, 3, 4, 5, 6, 7. There are 7 numbers is given. Okay. So now how to form the tree? So initially tree is empty. Now we insert this 3. 3 will be the root, and then we insert slowly. So A1. So this we have to insert 1. So we start with the root. 1 is less than 3. So we will go to the left part of the tree. Left part is empty. So we will insert there. 8 is greater than 3. Then 2, we start with the root. 2 is less than 3. So we will go to the left part of the tree. Then again 2 is greater than 1. So we will put it here. And then 6 is greater than 3 but less than 8. So we will put it here. Then 7 is greater than 3 but less than 8, again greater than. So we will put it here. Then 5 is greater than 8, greater than 3 but less than 8, but again less than this. So this is the structure of the tree. So basically this is the BST insert. So BST insert means, so if we just write the BST insert code, BST insert. So we first start with the root. So we take this x as a root of the tree. Initially root is empty, root is null. So while we are not reaching to a null, while x is not null, so we do this. If the key of x, that means key means here the values. If the key of x, so we are going to insert some number ai. If key of x is less than ai, then we call this is the recursive call. Then we go to then x is, this is while loop, then x is left of x, else x will be the right of x if key is greater than this. So that means we start with the root. If the root is empty, that is the initial condition, t is empty, then we insert that. That is why 3 is inserted here as a root. And after that we start with we say 8. So we know 8 is greater than this. So we call this in this, and then again 8 is sitting here. So like this. Okay. So this is the BST insert. Now what is the Inorder tree walk? Inorder tree walk is basically, so Inorder tree walk. So Inorder tree walk is basically, we first so x is the root of t. Okay. So we first traverse the left part of the left of x, then we print the root, and then we print the right of x. Print means we again call the Inorder tree walk. So we do until it says no child, then we print it. Print right of x. Print means this is basically Inorder tree walk again. So for example, here we start with, we want to call it, so this is our tree. After this insert, BST insert. Okay, so we start with the root. We first call this Inorder tree walk of this, and then we print 3, and then we print the right part of the tree. Okay, this is the right part. So again for the left part, so this is the tree now. So, now we again call the inorder. So, this has no left part. So, this is 1, then we print the right part. And similarly for this tree, so 8 is the root for this subtree. Now, we call the inorder tree walk. So, it will 8 will be, so there is no right subtree. So, 8 will be printed here and this has to be print the left subtree. So, left subtree is this one. So, again for this we call, this is the root, this is the right and this is the left. So, 5, 6, 7 sorted. Okay, so inorder tree walk, if we do the inorder tree walk on this BST, we are getting the sorted array. So, this is called BST sort. Okay. So, now we have to analyze this, how much time it is taking. So, how much time it is taking? How much time it is taking to do this inorder tree walk? It is order of n, because basically we are just seeing the node only once. We are just traveling the tree. So, we are visiting the nodes only once. So, there are n nodes. So, it is basically order of n, we are just printing the nodes. So, order of n. Now, the question is how much time it will take to build the tree, build the BST. This is the build the BST. Okay. So, how much time it will take? So, time to build the BST. So, that is the question. So, that time will depend on this, the total time for the BST sort. So, how much time it will take to build a binary search tree or for a given n input, for a given n array. Okay, so how much time it will take to build a BST? So, we will come back to this example again. Okay, so time to build BST, binary search tree. So, any answer? I mean, so any lower bound or upper bound? So, any upper bound, how much time it will take? So, how to build a BST? So, basically time to build a BST is basically summation of the depth of x, where x in the tree, because so we are every time we are comparing and we are reaching to a position, and that position is the depth of that node. Okay. So, depth means that many times we compare to insert this node. So, this is time complexity to build the BST is basically time of the depth of x, where x is in the tree. Okay. So, this will be basically big omega of n log n. This is the lower bound. We cannot do better than big omega of n log n. Why? Because when is the best case for this? When we have a balanced tree. If the tree, it depends on the nature of the tree. If the tree is balanced, if the tree is balanced, suppose there are n nodes, this is a balanced tree. If the tree is balanced, now how much time it will take to insert, how much time it will take to build such a tree? So, how many nodes are there here in the leaves? So, there are basically n by 2 nodes. There are total n nodes, and this is the height. Height is basically log n base 2. Okay. Now, this is the depth of this node. This depth is log n. So, for each of this leaf node, we had to compare root, then this with this, then only it came here. So, that is the depth of this node. Depth of this node is log n. So, at least for each of this node we have to compare log n time. So, n by 2 is n by 2 log n is the comparison for all this node, and even we have this node. So, that is why height must be, so time must be greater than n log n. So, this is the depth. So, this must be greater than n log n, because there are n by 2 nodes. So, at least for this node we have to the depth is log n for this node. So, depth is log n means they had to compare with this node, this node. So, how many comparison? At least log n comparison. each of these leaf had to compare with the log n many nodes. So, that is why we inserted in that height level. Okay. So, that is why this time is basically big omega of L log n. So, this is the lower bound, we cannot do better than this. Okay. And any upper bound, whether this is any big O, so this we have to think. So, this is the best case. Now, can we say this is n square, big O of n square. So, when is the worst case of this scenario? Worst case is if the tree is bad tree, like if the tree is like this, if there are n nodes, then the height. So, then what is the summation of depth of x? X is in tree. So, this is basically arithmetic series. So, this is n into n plus 1 by 2. So, this is order of n square. So, if the tree is bad tree, so that means if our numbers are ascending order or descending order, suppose we have given numbers are like this, say 2, 4, 6, 7, 8, 9, suppose this is our input. Suppose this is our input sorted, our array is sorted already. Then what is the tree? Tree will be like this. So, 2, then 4, 6, 7, 8, 9, 6. So, this is basically to form this tree we need order of n square, because everybody has to compare with the previous all the elements. Even if it is reverse sorted also, this will be like this. If it is reverse sorted, the tree will be looks like this. Okay. So, this is the worst case. So, worst case is order of n square to build the tree. So, this is the time complexity for time to build the tree. Okay. So, this is the worst case. So, that means so this will be the time for BST sort. Okay. So, this will be the time for BST sort, because Inorder traversal will take linear time, and this will take the measure time will take by here to build the BST, to build the binary search tree, and that itself is a it is taking the time of order of n square. So, the time complexity for BST sort in the worst case it is order of n square, and in the best case it is order of n log n. So, the time for runtime or time complexity of BST sort, so worst case it is order of n square, and the best case it is n log n. Okay. So, BST sort, this is a sorting algorithm which is taking worst case order of n square and best case n log n. So, is it remind us some sorting algorithm we know whose performance is like this, like worst case is n square and the best case is n log n, n log n. So, we know any sorting algorithm we have studied comparison based sort, because here this is also the BST sort is also comparison based sort, because this is also a comparison based sort, and that is why lower bound has to be more than n log n. I mean that is why we cannot do better than n log n. We have seen by the decision tree method model that we have seen any comparison based sort worst case time complexity is more than, cannot be faster than the n log n. So, this is also comparison based sort, because we are comparing the element and then we are forming the tree and then we are doing the Inorder traversal. Okay. So, any comparison based sort we know having this time complexity, yes, quicksort. So, quicksort is having same type of time complexity. Worst case, quicksort worst case is order of n square and the best case is order of n log n. So, quicksort is having the same time complexity as BST sort. So, that is the our next point to see whether is there any relationship between quicksort and BST sort, why they are giving us the same time complexity. So, that we want to see that what is the relationship between BST sort and the quicksort. To see that, let us take the example again and we will see that they are having same number of comparison we are doing in quicksort and the BST sort. So, let us take that same example, a array. So, 3 1 8 2 6 7 5. This is our given input, and in the BST sort we form the tree 3, then 1, then 8, then here 2, here 6, and then 5, 7. So, this is the BST binary search tree, and then we do the Inorder traversal to have the this thing, to have the sorted one, to have the sorted array. Okay, so, this is the BST sort. Now, let us talk about quicksort performance on this input. So, in the quicksort what we are doing? We are choosing a pivot element. Suppose we choose the first element as a pivot. If we choose the first element as a pivot, so what will be looks like? So, 3 is a pivot. So, what pivot will do? Pivot will partition this array into 2 sub array. All the element less than x must be left sub array, all the element greater than x must be right sub array. So, that way it will do like this. So, 3 this is the array 3 1 8. So, let us just 3 1 8 2 6 7 5. So, this is the given input. Now, we choose this as a pivot element. So, it will partition this into 2 parts. All the element will be less than x must be in the left sub array, all the element greater than x must be in the right sub array. So, who are the element? So, 1 2 must be sitting here and 8 6 7 5. So, this is quicksort partition, and here we are assuming one thing, this partition must be stable partition, because we are assuming this ordering will not changing. So, we know this is 1 2 will come in the left sub array, but it is not guaranteed that 2 will come. So, which ordering? But here we are using a partition which is called stable partition, and that is not very tough to get the code of stable partition. So, stable partition means we are assuming the ordering of this input ordering is same as in the array. So, they are 8 6 7 5, they are in the same order. Okay. Now, again for this we are taking this as a pivot. Now, all the elements, so 2 will be sitting here, and we are taking this as a pivot. So, who are the element are greater than, all the elements are greater than less than 8. So, 6 7 5, then 2, then nobody is there, then we call 6 is here. So, this is basically 5 and 7. So, this is the recursive call of the partition. Now, if you just form the tree like this, so like this, if you look, these two trees are same. So, that means we are doing the same number of comparison. So, in the partition, recursive call of the partition, the number of comparison we are doing is same as to form the BST, because to form the BST, this 6, when you insert 6, 6 has to compare with 3, 6 has to compare with 8. Here also, so to come here, 6 has to compare with 3, because this will partitioning into 2 parts, again 6 has to compare with this 8. So, the same number of comparison we are doing for the both the cases. So, this is the idea. So, BST sort, So, this is the observation. BST sort basically to form the BST performs the same number of, maybe in different order, but we are doing same number of comparison as in quicksort, same comparison as quicksort. Okay. So, that is the reason they are giving the same time complexity. Their time complexity is coming out to be same because of this fact that we are basically doing the same number of comparison in both the cases to form the BST and for the quicksort. Here we are assuming this table, the partition is stable partition, because to, and that is also not tough to achieve, to have this, to show the same tree we are having this. So, this is the observation, and that is the reason it is giving us the same time complexity for the BST sort and the quicksort. So, in the next class we will talk about randomized version of the BST sort, and there we will see the height of the randomly built BST. So, that will expected height we will see to be balanced log n. So, that is the that we will cover in the next class. Thank you.